All right, so this is in a sense, a big day in the class because the mole is such a fundamental concept. You probably think, well, chemists make too big a deal out of mole. Well, look, I got my molar eclipse shirt on, okay? And I don't just have one mole shirt. I have an entire wardrobe. Moles of the round table. Here, I need to give you these because I'm taking, excuse me? I need to give you these because I'm also taking attendance at the same time. Right here. There you go. Yeah, what year is this one? 2012. I picked this one out. Well, I just felt like it went with my black shirt. And it also, we just had an eclipse, right? Molar eclipse. 2012. Moles of the round table, 2011. Mole of animals, and I don't even know what year that one is. And the animals. Here's 2010. Moles of the Caribbean. I didn't just have these made up specially for me. Okay? They sell these shirts. Here's National Mole Day. What year is this one? This is Moleween. You can't see the year. And obviously I don't have it memorized. But you notice the date is keep popping up. October 23rd. October 23rd. There's a lot of significance to that. All right, where do we get that? Where do we get October 23rd? Well, what is a mole? Now convert that into a date. October 23rd. And then what you'll see on some of these shirts, like, see if I get an example here. This one isn't quite perfectly accurate. It says it begins at 6 a.m. It doesn't begin at 6 a.m. It begins at 6:02 a.m. All right? 6:02 a.m. till 6:02 p.m. That's Mole Day on October 23rd. That's my favorite one right there. Well, why is that your favorite? Hardly has anything on it. Hardly has anything on it. This is a Texas shirt. These come out of Flint, Michigan. Flint, Michigan. I told you I used to work for Dow Corning Corporation, Silicones, headquartered in Midland, Michigan. Not Midland, Texas, Midland, Michigan. And Flint, Michigan is about 10 miles to the east of Midland, Michigan. So someone probably from either Dow Corning or Dow Chemical retired from there or whatever and has set up the headquarters for Mole Day communications and the Mole Day website, and I think they run a little contest to make a new shirt each year, and I haven't seen the one for this year, and it's kind of getting late for us to order these. So hopefully by October 23rd, I'll have the 2017 shirt. I think right now I have from 2007 to 2016. So that's what I have. If this goes on and on and on, I don't know where I'm going to put all these shirts. All right, so that's the mole. What is a mole? This is some of the things we're going to cover. The mole concept. Oh, your battery is running low. I can't believe it. Here's some of the things we're going to cover. The mole concept of atoms and molecules, moles and compounds, converting from moles to grams, grams to moles, moles to atoms, moles to molecules. Okay, so we need to kind of get comfortable with what it is we're talking about here. And I'm not going to draw your attention to this, but you can kind of, did everybody get one of these? This is a listing sheet. Who needs one? You can kind of follow along. Every so often I'll look down here and we'll do a certain problem. And you can kind of fill in some of these blanks, walk away with some of the basics. All right. So what is a mole? Well, we've seen that number. And that's basically what the mole is. It's a number. It's a number. Don't take it any further than that right now. What is a dozen? What's a dozen? 12. 12 what? 12 anything. Depends on what you got a dozen of, right? You got a dozen eggs, you got 12 eggs. If you got a dozen donuts, you have 12 donuts, right? So what is a dozen? A dozen is a number. It's a word we use for a number. What is a pair? Two. Got someone over here who wants to be fun. It's a piece of fruit, right? Okay, a pair is two whatevers. 2 shoes, 2 turtle doves. Okay? All I want you to see, we're just talking about a number. So, first blank, a mole is a number. It's what it is. The mole is a very large number. And this is the number. Now, you're going to see it that way. On a few occasions, you'll see me take it out to 4 significant figures. All right, it's not an exact number. There's more significant figures here. If you were doing a really, really careful calculation, you would look up this exact number and flesh it on out, a few more significant figures. So, and there will be one calculation where we'll go to this because I want to make a certain point and want to get to a certain number. But we'll generally be looking at it as 3 significant figures. So it's a very large number, 6.02 times 10 to the 23rd. It is referred to as Avogadro's number. Avogadro, you'll see his name come up again when we get into the gas laws. But Avogadro, and the capital letter N is sometimes used to refer to, not often, but sometimes it will pop up, that it's representing this number, 6.022 times 10 to the 23rd. 1 mole of atoms is 6.022 times 10 to the 23rd atoms of that element. 1 mole of water molecules is 6.022 times 10 to the 23rd water molecules. A mole of sodium ions is 6.022 times 10 to the 23rd sodium ions. I see you get the point. It's a number. And if we mention a mole of something, we're mentioning that many of those things. Whatever the substance tends to be, a molecule, an atom, an ion, doesn't matter. It's going to be that many of them. 1 mole of them is always that number. We haven't gotten there yet.
Okay.
Yeah, let's talk about molar mass in a minute. I'm going slow here first because I just really want you to appreciate this. Sometimes I write this out on the board, and maybe I will, just so that you, when I say it's a very large number, I want you to appreciate what I mean by that. So let's say let's do 602. The decimal point is right here, times 10 to the 23rd. So to really see the magnitude of this number, we need to move that decimal point over here 23 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20, 21, 22, 23. Just made it. Okay, well let's just look at how big that is. There's hundred thousands, millions. Right here we're into the millions. Here's billions. Okay? Now we're into the number of hamburgers McDonald's sold. Trillions. Where are we here? What do you know that's got that order of magnitude? Trillion. The U.S. debt. It's the answer I always get. And let's hope it doesn't flop on over into here, because we don't even know what to call this. Here's trillions, quadrillions, I guess it is, quadrillions. All right, so what you're seeing right now is the mole is a bigger number than the U.S. debt. I always thought if I get elected to Congress, which I'm not planning to, but if I did, I would stop reporting what the U.S. debt is in trillions of dollars. And I would start saying that that's our debt. I'd start reporting it in moles. All right? I'd say, oh, wow, I feel a lot better. Don't you feel a lot better? I don't know what it is. I just pulled a number out, but I probably need a few more zeros there. But in moles, the U.S. debt is just some little, very small decimal point. All right? I just want you to get a feel for how big this number is. So we're in quadrillions. And here we're in I don't know what. And then we finally get up to here. So really what we could say, if you look at right from here, that a mole is like 602 million trillion. That's what it is. It's 602 million trillion. You take 602 million and multiply it by a trillion and you got a mole. Now why has it got to be such a big number? Because atoms are such tiny things. And if I want to go over in the lab here and work with if I want to go work with copper, and I say, well, how many atoms of copper I want to work with? I'm going to need to be working with that many atoms of copper to really get to the point where I can accurately weigh it in the laboratory. 602 million trillion copper atoms, we will see in just a second, weighs about 63 grams, 63 and a half grams. I mean, you can hold that in the palm of your hand. You can hold 602 million trillion copper atoms in the palm of your hand. A penny is not a mole of copper. You probably need about 20, 30 pennies. 20, 30 pennies would probably be a mole of copper. Something like that. We could figure it out. We could go weigh a penny. I have weighed a penny. A penny weighs about 2.3 grams, something like that. So we would need about 30 pennies, 25 pennies, and we'd have a mole of copper. Okay? So you can see how tiny even the copper atom's not the lightest atom on there. It's not the heaviest, but it's a pretty good size atom. Has some weight to it. you need a whole lot of them before you can start weighing them in the laboratory. And that's what we're doing with the mole. We're bringing into the macroscopic world that we live in a number of these atoms and molecules and that sort of thing that we can start to work with and react with one another and know how many atoms we're working with. We need to know in a particular reaction how many of different things are we working with. Exactly how many molecules do we have there? How many atoms do we have there? How many ions are there? So that's what this does for us. This is a little, can you turn this light off for us, please, for a second? This is just making the point, if you had two different marbles, red and yellow marbles, and the yellow marbles were only 4 grams and the red ones were 7 grams, you could have the same exact number of red and yellow marbles, but they're not going to weigh the same. The 12 red ones are going to weigh 84 grams. The 12 yellow ones are going to only weigh 48 grams. You have the same number. You have a 1-to-1 ratio of red and yellow marbles, but the red ones, you need 84 grams of them to know that you have 12 of those marbles. Likewise, if you move on over into iron and sulfur, 2 different elements on the periodic table. Iron is heavier than sulfur. So I could have 55.85 grams of iron and I would have a mole of iron. What does that mean? I've got 6.022 times 10 to the 23rd iron atoms. Well, to have that same exact number of sulfur atoms is only 32.07 grams of sulfur. So that little pile of iron, that pile of yellow sulfur, have the same number of atoms in each pile, but they don't weigh the same. So we can't just rely on weight and say, oh, let's go get 5 grams of iron and react it with 5 grams of sulfur. So, well, you can do that, but you don't have an equal number of atoms of iron and sulfur. You follow me? And what did Dalton say? Dalton said, going back to Dalton and our atomic theory, he says, atoms of one element react with atoms of another element in small whole number ratios. He didn't say they react with one another gram to gram. They react with one another atom to atom. Okay? So if these were atoms, one of these would react with one of those to form a molecule, a red and yellow, an atom of the red and an atom of the yellow. We would get 12 molecules out of there. But they're not reacting gram to gram. They're reacting atom to atom. And every one of those atoms has a different weight. So that's where we got to get to with the mole. All right, you're starting to see a little bit of the molar mass here. This is molar mass. This is the mass in grams. The mass in grams of 1 mole of any substance, any particular substance. That's its molar mass. All right, so I've already mentioned mole day. I think I mentioned most all of this. So 1 mole. 1 mole of, I want to do a calculation here for a second. if we look at the periodic table, let me just come out of here for a second and do a little calculation. Let's take carbon. Carbon's the one. So I'm going to just, what do we see on the periodic table? We see a C for carbon. We see a 6. That's an important number. Atomic number, number of protons. We see the average atomic mass. All right. Now, really, fundamentally, at the atomic level, what we are saying is that a carbon atom weighs 12.01 atomic mass units. This is one atom. So what I want to do a calculation right now with you is what would be 1 mole of carbon atoms. That's going to be 6.022 times 10 to the 23rd carbon atoms. Put an A in there. I mean an O. All right, let's see what 6.02 times 10 to the 23rd carbon atoms would weigh. Now, the periodic table that I give you right here, mass units, it says 1 atomic mass unit, 1 AMU, equals 1.661 times 10 to the minus 24th grams. So, this is a calculation that I wouldn't necessarily have you doing on a routine basis, but I want to do it once to make a really important point. So let's go through this with dimensional analysis. I want to know what 6.022 times 10 to the 23rd carbon atoms would weigh in grams. Okay, so here's what I'm starting with. I got this many carbon atoms. And they weigh 1.661 times 10, make sure I'm getting this right, times 10 to the minus 24th. Is that what an AMU is? Grams per atomic mass unit. That's my conversion factor. Wait a minute. Am I doing this right? So then that would give me hang on a second. I hope you're doing this in pencil. I got to think about what I'm doing. Grams per atomic mass unit. No, I'm sorry. I'm sorry. You doing this in pencil? I'm starting out wrong. What do I know? What do I know to start with? This is what I know. That it's 12.01 atomic mass units per carbon atom. That's what I know. So I'm starting with. What is the weight of a carbon atom? 12.01 atomic mass units. Sorry, I got heading down the wrong path right at the beginning here. So I got 12.01 atomic mass units per carbon atom. Everybody with me so far? I've got to kind of back up and start over again. So now I bring in I want to convert my atomic mass units into grams. So I have 1.661 times 10 to the minus 24th grams per atomic mass unit. And now I've converted that now to grams per atom. I wouldn't know what how many grams one atom weighs. I'm not going to do that calculation right now. What do I want to know? I want to know grams per mole. I want to know how many grams there are in 1 mole of carbon atoms. So how do I do that? Well, there are 6.022 times 10 to the 23rd carbon atoms per mole of carbon atoms, right? And my carbon atoms cross out. And the only thing left now is grams per mole. Now I would recommend that you do this calculation right now so that you can get used to using scientific notation with these large, and in this case a negative exponent, 10 to the minus 24th. So take out your calculator and do this calculation. And we'll put the number down here in a second, but make sure you're looking at a number on your calculator. 0.01. Okay, now the answer you should get is 12.01, if you round it off, grams per mole. If you're not getting that, let's get that. Are you getting that? You got it? Guys getting it? You got it? The TI-30 and the TI-80 series handles it differently. You got it? Okay. Just want to, if you're having trouble getting, if you have trouble getting it, sometimes it's good to wrap these in parentheses so that you don't end up multiplying by 10 to the 23rd when you should be dividing by it or whatever. Wrap them in parentheses. All right? Well, that number looks familiar, right? The one atom is 12.01 atomic mass units, and 1 mole of those atoms is 12.01 grams. All right? So what I want you to appreciate right away is how powerful this is. We got numbers on here, and you can see there aren't units. When we have the average atomic mass, it doesn't have a unit. If you're talking about an atom of that element, an atom of that element is going to be that average atomic mass in atomic mass units. And if you're talking about a mole of those atoms, it's going to be grams. All right? And that gets you right here. That's what the point of this is right here. 1 carbon atom is 12.01 atomic mass units. 1 mole of carbon atoms is 12.01 grams of carbon atoms. And if you want to prove any of these, feel free to go do that calculation for iron or sulfur or whatever. You're just starting out with this, 55.85 atomic mass units for the iron atom. But if you do, just plug that into this equation right here, put in the 55.85 here, and run that through the calculation, you're going to get 55.85 grams per mole of iron. All right, so this calculation works for everything on the periodic table. And that's the power of it. This is the molar mass of carbon. What's the molar mass of carbon? The molar mass of anything is the mass in grams of 1 mole of that substance. So we're looking at molar masses here. This is the mass in grams of 1 mole of carbon atoms. These are molar masses. Okay, now let's just pause. Right there, you're just looking at atoms off the periodic table. But now we come right here to a very simple molecule, O2. The oxygen we're breathing, the air we're breathing, has oxygen in it in this form right here, O2 molecules. That's what you're breathing. You're not breathing oxygen atoms. You're breathing O2 molecules. So we chemists, we keep track of exactly what it is if oxygen ends up being a reactant in a chemical reaction. We are looking at it as oxygen, O2. And so notice what you got here, that let's work with this right here. Oxygen is 16.00 grams per 1 mole of oxygen atoms, and there are 2 oxygen atoms per O2 molecule. You with me? That's how we're getting here. An O2 molecule contains 2 oxygen atoms. So it's going to be twice as heavy as 1 mole of oxygen atoms. It's going to be twice as heavy, 32.00 grams of O2 per mole of O2. That's how we're getting there. So whenever we have a formula for anything, and here's a very simple one, a diatomic molecule, O2, we have to take into account that there are 2 atoms in each of those molecules and figure it out. So the molar mass of oxygen atoms is 16 grams per mole. The molar mass of O2 molecules is 32 grams per mole. The molar mass of a mole of that substance, O2 molecules, is 32 grams. Okay, so that gets us to this molar mass. Let's do a couple of these problems. Those of you that may not have heard me say this listening sheet, most of these problems I copied and pasted right out of Chapter 4, Homework 1. All right? So we won't do all these in class, but some of these that we do. So let's... and they represent certain things. So you get over here, here it is. How many atoms are there in 2.95 moles of helium? I know what would have been beautiful is if I could give myself more space here. How can I do that? A little bit more. There we go. All right, let's see how we would approach a problem like this. What do you know? You know that 1 mole equals 6.02 times 10 to the 23rd. I didn't say 1 mole of what? Just anything. Now, question 2 is saying, how many atoms are there in 2.95 moles of helium? How many atoms are there? So I have 2.95 moles of helium, and I want to know the number of atoms. of helium. Well, I know there are 6.02 times 10 to the 23rd helium atoms per mole of helium. Moles of helium cross out. And I really want to encourage you to use dimensional analysis, particularly in Chapter 4. Dimensional analysis will become your best friend if you use it routinely and get comfortable using it. I've got that conversion factor up there. 1 mole equals 6.022 times 10 to the 23rd. How do I use it in this calculation? Do I multiply by it? Do I divide by it? Well, I've got 2.95 moles of helium, so I'm going to put moles of helium, moles, in the denominator. And I'm going to put the number, Avogadro's number, in the numerator. I mean, here's our conversion factor up here, which could say 1 mole of helium equals 6.02 times 10 to the 23rd helium atoms. There's our general conversion factor, but now we're in a specific case right now. We're talking about helium. So we're talking about Avogadro's number of helium atoms. So do that calculation. So something like 1.78. 1.78, you can round that off to 3 significant figures. Why? There's 3 significant figures right there. And you can see why I just bumped back down to 3 significant figures on Avogadro's number. I'm not going to be going, and it's 10 to the what? Times 10 to the 24th atoms. Okay, number 3 is very similar, but you have to be a little aware of what's going on here. It's asking how many atoms are there in 6.36 moles of diatomic nitrogen. And notice in problem 2 and now in problem 3, we're not even getting involved at all in how much does this weigh. There hasn't been any question yet about how much does it weigh. We're just saying how many are there. How many are there? Don't worry about how much it weighs. So this number 3 is going to be very similar. We're going to start out with 6.36 moles of nitrogen. And there's going to be 6.02 times 10 to the 23rd nitrogens per mole. Now, what else do we need to do? It's asking how many atoms are here. How many atoms of nitrogen are there in an N2 molecule? 2. So we need to bring that factor in here. There are 2 nitrogen atoms per N2 molecule. All right, so in problem 2, helium was a monoatomic element. It floats around as helium atoms. It's not diatomic. But nitrogen is diatomic. So we need to convert the the moles of nitrogen to number of nitrogen molecules, and then we got to multiply it by 2 in order to get the number of nitrogen atoms. So what would you round that off to? 3 what? Someone have a number? Oh, it's not 3. It's not 3. I didn't multiply it by 2. What is it? 7.66. I didn't do it. I didn't multiply by 2. So it's 7.66 times 10 to the what? 24th nitrogen atoms. And I would like to see all of this. All right? Here's, you got a number, but what is that number? That's nitrogen atoms. Pay attention to problems. Now, this could have said, how many molecules of diatomic nitrogen do you have here? So you got to read carefully here. This is a molecule, but each one of those molecules has 2 atoms in it, okay? So you got to read the problems carefully and answer. Say, understand, before you try to solve a problem, really understand what is the problem. What are you being asked to do? Okay, now what I've told you is every one of these problems is kind of a different case. Look at number 4. Calculate the number of moles of cerium represented by 2 times 10 to the 24th atoms of cerium. This is what you are given. This is what you're being asked to calculate. Cerium, that's cesium. Where's cerium? Where is cerium? Oh, down there, way down there. Number 58. See, I'm not very familiar with that element. Yeah, number 58. So moles of cerium, Ce. We are given 2.00. Somehow my font size on my pen got jumped up real high. Times 10 to the 24th cerium atoms. Well, just take a look at this before you even try to solve it. I've got cerium atoms here. I want to end up with moles of cerium. So I'm going to need moles here and cerium atoms down here, aren't I? Can you see that? Cerium atoms has to come down here. So without even figuring out what to do here, this is unit-wise what I need to get to. I need to get to this point so that cerium atoms can cross out, and I've converted it to moles. So what do you know about the relationship between moles and cerium atoms? What is that relationship? It's not 1 to 1. 1 to that. So 1 mole of cerium atoms is 6.02 times 10 to the 23rd cerium atoms. I kind of walked through this that way just to show you that dimensional analysis has shown me that I need to divide by this number. Okay? Up here we were multiplying by the number. You are going to want to know when to multiply and when to divide. And dimensional analysis will tell you. if I multiplied this by 6.022, or 6.02 times 10 to the 23rd cerium atoms per mole, I would get cerium atoms squared per mole, which is nonsense. It's a meaningless number. Okay? It's just nonsense. So look at your units. Look at your units. I saw cerium atoms up here, so I need to get cerium atoms down here. And what is that relationship? 1 mole of cerium atoms is 6.02 times 10 to the 23rd cerium atoms. So now we're dividing. Before you divide it, let me ask you a question. Now here's the other thing I do with problems. You should have a little bit of an appreciation, idea of what is going to be a reasonable answer. Now you tell me, before you even look at your calculator, is this number going to be greater than 1 or less than 1? Greater. Why? Why is it going to be greater than 1? You got 10 to the 24th right here, right? You got 10 to the 23rd down in the denominator. This number is smaller than that number. So it's going to go into that number at least once and maybe a little bit more. You follow me? I can look at that and say, this number should come out greater than 1. So let's see if it comes out greater than 1. Something like 3.32. Okay, now if you're not getting greater than 1, and you might not be, make sure you do this. Wrap this in, here's where it really is important. Wrap it in parentheses. Because otherwise, sometimes what the answer comes out with is you've taken this number, you've divided by 6.02, and you've multiplied it by 10 to the 23rd, and you get this huge number. Okay? So the answer is, if you didn't get 3.32, then do it again. Do it again, but wrap that in parentheses when you do the division. Okay. All right, so far we've just been working with the concept of moles and atoms. And, you know, I've got this many moles of something, how many atoms do I have? I've got this many atoms of something, how many moles do I have? And you're working off of this number, Avogadro's number. That's your key conversion factor between moles and atoms, or moles and molecules. We could be asking the same question about molecules of water or molecules of oxygen. Same conversion factor, Avogadro's number. Okay, let's do number 5. What is the mass in grams of 6.02 moles of niobium atoms? Well, before we even try to solve this, how much does a mole of niobium, we got to find niobium on here. What's the atomic number of niobium? 41. Niobium, 41. So what does a mole of niobium atoms weigh? What's the molar mass of niobium? 92.91. So 1 mole, and niobium is Nb. It's not Ni, because that's nickel. Nb is 92.91 grams. So it's really 92.91 grams of niobium per mole of niobium. And what do we want to know? We want to convert that into grams. Oh, I'm sorry. What do we know? We do know that, but this is what we're starting with. We have 6.02 moles of niobium. All right, let's just pause here a second before we even get bogged down in numbers. We want to convert moles to grams. So what units need to be here? Grams per mole. All right, we need to get moles down here and grams right there. See, I don't even get bogged down in the numbers. I need grams per mole. How do I know that? Because I want to get rid of that unit and convert it into grams. And we know that it's 92.91 grams per 1 mole. So the dimensional analysis is telling me to solve this problem, I need to multiply moles by grams per mole. And what do you get? We can stick with just 3. We got 4 significant figures here, but we have 3 here. It's kind of funny to use the number 6.02. Looks like Avogadro's number, but this is how many moles they have. Okay, this has nothing to do with that. How many moles of niobium they happen to have. So 550, what do you get? 559 is fine. Okay? Now, I mean, we could go on and do 5 more problems like that. You may find in the chapter 2 or chapter 4 homework 1 that there are 5 or 6 problems just like this one, where you've given moles and you need to convert it into grams. Yeah, I'll let you figure out number 6. We've dealt with nitrogen up here in number 3. Just pay attention to what we did in number 3, and you should be able to sort out number 6. Let's look at number 7. Yeah, and then I think I want to. Let's see. Can we do number 7? Yeah, let's try to do number 7. We've got 2.16 times 10 to the 18th nickel atoms, and they want to know the mass. Well, in this particular case, you're going to need to know. You're going to have to deal with 2 things. 1 mole of nickel is 6.02 times 10 to the 23rd nickel atoms, and 1 mole of nickel is how much does 1 mole of nickel weigh? Okay, you get these right off the periodic table. And I always start over here with what I'm given. I try to. I messed up a couple times this morning where I didn't start right here, but this is what we're given. We're told we've got this many nickel atoms, and we want to know how many grams. What would that weigh? What would that many nickel atoms weigh? All right, now that problem, number 7, we're going to convert the number of atoms. Here's the strategy. We're going to convert that into moles, and then we're going to convert that into grams. You already know how to do these two things. You know how to do these two things. You know how to go from moles to grams. You know how to go from atoms to moles. But since we're starting out with atoms, we need to get to moles and then convert it to grams. You follow me? And I set these things up. I don't do them as two problems. I just set them up. I don't know if I'm writing small enough to do this. So we've got that, and we know that there is 1 mole is this many atoms. Those atoms are going to cross out. We're going to be right here. We've converted that many atoms of nickel into moles of nickel. 1 mole of nickel. And then I'm going to put mole down here so that I can cross that mole out and grams in the top. So I'm going to have grams per mole, and it's 58.69 grams per mole. Okay? And I'll leave it to you to calculate that. All right, one other, we've got 5 minutes, and so we can come back and look at 8, 9, 10, 11, 12. 12 is probably what I like to do. I wish I had a little more space right here. I'll maybe write this on the board. Look at number 12. It says calculate the formula mass and the molar mass of this compound here, lithium sulfate. So far we've just been dealing mostly with atoms, nickel, niobium, etc. Some simple molecules like nitrogen and oxygen. But now we have this ionic compound, lithium sulfate. So let's go over here and look at lithium sulfate, and we'll come back and answer these questions here. So we've got lithium, Li2, SO4. All right. We've got to figure out what the molar mass of this is. Now here's how you do this. You got your periodic table in front of you. Lithium. I got lithium right here, and I look at my periodic table. Help me here. What is the mass? What is the molar mass of lithium? 6.94. So it's 6.94 grams per mole. And there are 2 lithiums in this formula. So what's that? Give me that product. 13 point what? 88. So we'll say 13.9. We've got sulfur, 32.07. I'll tell you what, let's go back to 88. I'm sorry. Yeah, we got these out to 2 decimal places, so let's do it that way. 13.88. Sorry, I rounded that prematurely. And I only multiplied it by 1. I'm looking at the formula. There's only 1 sulfur in this formula. Oxygen is 16.00 times 4. Now you're going to add all of that up. We want to know what 1 mole of lithium sulfate would weigh. I actually I could have stayed here with atomic mass units. Yeah, I could have stayed with atomic mass units. Because Li2SO4, that formula unit has 2 atoms of lithium in it it has 1 atom of sulfur in it and it has 4 atoms of oxygen in it. So we got all that. Let's add that up. 7 and 8 is 15. 9. So 5 and 4 is 9. Am I adding this right? 9, 10. Is that what you get? 109.95? So lithium sulfate is 109.95 atomic mass units. That is the mass of 1 formula unit, which would be 109.95 grams per mole. If we did the conversion from atomic mass units to grams, it would be just like we were doing with carbon. That would convert over to 109.95 grams per mole. So your answer here is, where'd it go? So this is 109.95 atomic mass units, 109.95 grams per mole. Okay, now what I would recommend you do, you see right at the bottom of your page there, number 15, do this. Not right now. I'm going to dismiss you now. But you do what we just did with lithium sulfate, do that for calcium phosphate, sodium sulfate, and get the, it says determine the molar mass. You're going to be, molar mass is the mass in grams of 1 mole of that substance. So your answer here is going to be grams per mole. All right, we got a good start. We'll, where'd it go? There it is. This one? You're welcome. Did everybody get their test? You just have to do 1 day.
Be there for 1 day, so
Yeah.
Tuesday.
Yeah. What I'll do, I'll get a sign-up sheet. Monday, 10, 10:30, 11, 11:30. You know, I'll pass it around.
Okay.
And yeah, if you man that table for, and I'm not going to be there all the time. I got to teach, so students are going to be at the table explaining things.
Okay.
So I'll just have everybody, hopefully people will sign up. So we need about 16 people. We need 8 per day. So I need about 16 people.
Okay.
And no, you don't have to do it both days.
Okay. Understood.
And if someone even told me I can't come those days, I'd say, well, then you help with the preparation.
Okay.
You know, you help with prep on Friday or something like that.
Okay. I'll probably be there tomorrow from 9 to 11.
No, you don't need, it's just October. Oh, tomorrow for the preparation? Okay.
Preparation.
Yeah, good.